So we've seen an example of a vector field that is not conservative, and we'll see a little bit more, exactly why that vector field is not conservative in the remainder of this lecture, once we get to defining what's called the curl of a vector field. But let's do an example of a vector field which is, in fact, conservative. And this is a very, 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 very strong example, because it's coming directly from physics, and it describes a number of different situations in various physics. And this is what's called an inverse square law. And specifically, this is a type of law where the intensity of some quantity is proportional. This is typically the symbol used for proportional to 1 over the distance squared. And very often, an inverse square law in physics is what's called an inverse square force law, because where this typically comes up, and the first time you'll see this, is for forces between in two main scenarios in physics. The first is with a Newtonian gravitational potential. So a Newtonian gravitational force between two masses. A little bit later on, we'll use capital M for one mass and lowercase m for another mass. And another time we see the inverse square force law is with the electrostatic force. Between two charges, which we can call capital Q and lowercase q. This is really a great example of a conservative vector field, because the force field in either of these two cases is actually coming from the gradient of a scalar potential function. And because both of these are essentially described by the same mathematics, we'll just call that scalar potential function phi, where this scalar potential function is equal to some constant c divided by the distance between the two objects squared. R is the position vector with at the base. Its base is at. The potential is just the c over the distance squared between those two objects. So in the example of the gravitational force, if this is mass m and this is mass m, small lowercase m, then r, the displacement vector between m and m, is just this r right here. In the same exact picture for the electrostatic force. But this coefficient c, this constant c right here, changes depending on whether we're dealing with the electrostatic case or the gravitational case. But in either cases, this is the correct form or the potential energy, and specifically, we're going to show right now why this potential generates an inverse square law for the force. So the gravitational force, or the electrostatic force, between two objects is the gradient of this potential phi, and that's equal to the x partial derivative of phi, the y partial derivative of phi, this should be x, and the z partial derivative of phi. And it's convenient always to write the gradient vector of a function as, in this case, a 1 by 3 vector, but depending on what dimension you're in, it's going to be a 1 by whatever your dimension is vector, as a row vector. And so to evaluate this gradient, we have to go through and figure out exactly what each one of these partial derivatives is. Remember that 1 over the length of r, and we're putting our coordinate system at the location of one of these masses, mass m. So 1 over r will just be, in Cartesian coordinates, 1 over the square root of x squared plus y squared plus z squared. And therefore, when we go through and take, we'll just do one of these partial derivatives, call it d phi dx, will be equal to the x partial derivative of c times x squared plus y squared plus z squared to the negative 1/2 and therefore, by the power rule and the chain rule, this is going to be equal to c times negative 1/2 times x squared plus y squared plus z squared to the negative 3/2 times 2x, or d phi dx is equal to negative, we'll say c times negative x over the square root of x squared plus y squared plus z squared cubed, which is just negative c times x over the length of r cubed. And this is going to be exactly the same for the y partial derivative and the z partial derivative, only we'll have a replacement of y for the y derivative and z for the z derivative. So this is going to be equal to then negative c x over the length of r cubed negative c times y over the length of r cubed negative c times z over the length of r cubed, which can be simplified and rewritten as follows. And we're going to factor out some things here. We're going to factor out the c from the vector, negative from the vector, because each component has a -1. And we could factor out length of r cubed, but instead of doing that, I'm just going to factor out the length of r squared, and we'll see why in 1 second. This becomes negative c over the length of r squared times the vector x over length of r, y over the length of r, and z over the length of r. And you hopefully will see why we've written it like this, because this now says that the force is equal to negative c over the length of r squared. And this vector right here is a unit vector that points in the direction of the mass, in the mass example of the mass m. But in the charge example, if you repeat this picture but with charge capital Q and lowercase q, this vector is a vector r hat that points in the direction from the base vector, or the base object, to the other object. This is exactly r hat. And this gives us exactly what we were talking about before, in that it's telling us that the force for either of these two cases is exactly this vector right here. So depending on what the sign of c is and the value of c is, that's going to directly determine the direction of this vector. However, we do have exactly that if we take the magnitude of this vector right here, the magnitude of r, or the magnitude of the force vector, if you go through and calculate this, well, the magnitude of this vector right here is going to be the absolute value of c, whatever that is, over the length of r squared. And so this gives us exactly what we started out looking for, which is that if we look to the magnitude of the force vector F, this is going to be exactly equal to the magnitude of this, which sure enough ends up simplifying to the absolute value of c divided by the length of r squared. You go through and calculate this magnitude, and this gives us exactly what we want. This is saying that the magnitude of force is directly proportional to 1 over the distance squared between the two objects. And this is a very neat example. If we go through and kind of look at what c is in each individual case, you can go through and kind of determine exactly what that's going to be in the gravitational case. You're hopefully familiar with c being equal to that gravitational constant, it's called, times m times m, so g times m, which will give you exactly the force law. The force is equal to, or magnitude of force is equal to g m over length of r squared. And sure enough, in terms of the direction that this is pointing, well, we know that c, the masses will always be positive, so c will be positive because g is a positive constant. And what this means is if this is mass m and this is mass m, then the force vector will be pointing negative in the direction of negative r hat. So in this direction right here. In the electrostatic case, it's a little bit more complicated, but it's not that much more complicated. The electrostatic case, c C is equal to negative electrostatic constant times charge 1 times charge 2. And electrostatic constant is positive. Charge 1 and charge 2 could both be either negative or positive, in which case we have different scenarios, right? If charge Q, the charge 1 we'll say is negative, and charge 2 is negative, or if charge 1 is positive and charge 2 is positive, this gives us that C itself is negative. And if C is negative, this is going to be good because this negative sign cancels this negative sign. And this is good because when we go through and look at a picture, say, of the forces, of the actual force vector between Q and Q, this force vector, C, is negative, the negatives cancel out, and the force vector is going to point away, which we expect if the charges have the same sign. However, in the opposite case, where the signs do not match, we have that C is positive. If the sign of Q and Q are not equal, C becomes a positive constant. And we have the reverse scenario where charges are being attracted to one another. Right, so there are many other areas where inverse square laws show up in physics, but this is a great example of showing a conservative force field, because it's coming directly from a very physical example. And not only that, we can actually go through and visualize this in the following way. So if we visualize this force field and actually go through and plug in what this force field is going to be, it's going to look like the following. And this is, you can see a plot here of this force field, this gradient vector field for this potential, where you can clearly see at any given point, if you move lowercase q, that charge around any given point, this vector field is giving you the force that you would experience at that point if q is located anywhere around this. And this is specifically for both charges being equal to one another. Obviously, the magnitudes and the values of this will change as C changes if the charges or the masses are different values. But this is just if for everything normalized to 1. So the next thing that we want to talk about is the topic of differentiation of a vector field and what it means to differentiate a vector field. And we mentioned before that this is a vector field is an object that is much more complicated than a scalar field. And the reason for this is for two main reasons, twofold. A vector field has both a magnitude and a direction, associated with every point. So because of this, actually defining the rate of change in a certain direction of this vector field is a little bit more complicated. We have to be a little bit more careful with how we do that. Whereas a scalar field, we can just use the gradient of that scalar field. A vector field, on the other hand, we have to be much more careful with how we define the rate of change. And it turns out that we actually have two main different rates of change that we can define for this vector field. In general, these different types of rates of change will give us a full picture for a given vector field about how it's changing. But these two types of rates of change are called the divergence and the curl of the vector field, respectively. And in some sense, the divergence gives you the amount of stretching or compressing a vector field is doing. And the curl of the vector field, so I'll do the kind of summarize this here. Two main types, or main ways of measuring the local rate of change, or say local change in a vector field. First one is the divergence of the vector field F. And to describe this in words would be to say that this is a scalar function which measures the total compression, and we'll say not total or net compression or expansion of F, vector field F, at every point. That's the divergence. And the curl of a vector field F, also sometimes called the rote of the vector field F, to denote rotation, is a vector field. So it's a new vector field. Remember, a scalar function is the same thing as a scalar field. So the curl of a vector field F is a new vector field which measures the total local rotation, or the net rotation of the vector field F at every point. And so these are the two things that we typically use to measure the rate of change of a vector field, and will give us a lot of insight into the changing of a vector field. So we'll start by defining the divergence and then move on to defining the curl of a vector field F. So to define the divergence, what we'll do is consider this picture right here. So first assume that what we're going to do is we're going to go through and give some motivation for why the divergence is defined the way that it is. And in order to do that, it'll be very convenient to apply some physical language here and actually consider a very physical example. So in this this motivation, you think of this as motivation for defining the divergence. Eventually we will define it as we move throughout this motivation example. But throughout this example, what we'll be thinking of is the velocity field for a fluid flow. Right. So let's say we have some sort of vector field that gives us a velocity field. So we'll say that we have a velocity vector field. We'll call this for short V, where this vector V is a vector of three functions, right, of vector in 3D, so a vector field in 3D. Each one of these, V1, V2, and V3, are functions of position in space and possibly time as well. But, so we have a velocity vector field, and what we'll consider is the flow of mass through this field, V. So specifically to do this, we'll consider what's called the behavior of the mass density function, rho of RT, where rho of RT is the mass density function. At any given point R, so any given point in three-dimensional space, and also in time as well, because if the mass is flowing with respect to time, this is changing with respect to time. Just a quick thing that we want to point out here. Remember that velocity has units of length over time, and the mass density function, because we're in 3D, will have units of mass over volume, or length cubed. And that'll be important to kind of think about when we're going through and doing these calculations here. So the next thing that we're going to do is we're going to consider an arbitrary point in this vector field, immersed in this vector field. And what we'll be considering is the flow of mass through a very small cube surrounding that point, or a very small rectangle. It doesn't necessarily have to be a cube. I've drawn a cube here, but each one of these things could be different. Delta x, delta y, and delta z could be different. The main idea is that we're assuming they're very small. So delta x, delta y, and delta z are all much, much less than 1. And what we want to do is get an idea of how to express conservation of mass inside this small cube. And so it's definitely helpful now to kind of maybe move over to two different vector fields, possible velocity fields, that we're going to kind of consider, and get kind of a nicer picture of this. So this cube here is immersed in some fluid flow field. So if we'll move back to that other example that we just talked about, just because I have the plot up, and we'll kind of look at what this picture looks like. So this is a picture here of the scenario that we're talking about, where we have some sort of small cube immersed in some vector field, and we're considering the flow of mass, right, through this cube. And what we want to do is try to express the conservation of mass in this cube. Try to do what's called a mass balance in this cube. In engineering class, you would call it a mass balance. But really, this idea is very fundamental to the differential, the derivation of both the idea of divergence, and also to we're going to derive what's called the continuity equation in the next couple pages. So the whole idea here is that this cube is very, very small, right? We're going to kind of go very, very small with the cube, as small as you can consider, right? And that's going to make certain approximations valid. And then we'll take the limit as that cube goes to 0. The size of the cube goes to 0. Right, so the idea here is that we have a very small cube. This is kind of a picture of a cube in this vector field with a side length value of 1. But we're talking a very, very small cube relative to the vector field in order to get kind of a good approximation of the vector field and not much changing of the vector field throughout the cube. Right, so even if I try and zoom in here, this is an h value of 0.007. It's very small. I'm going to make it a little bit bigger just to kind of show the picture here. But the idea is that we're taking the limit as eventually as this goes to 0. This cube gets really small. But so we'll consider the cube and the flow of the vector field through this cube. Another good example. This is, remember, this example right here for the gravitational field. This is what this vector field is. But you could consider this idea with any vector field that you can think of, as long as it's smooth, or its component functions are smooth enough in the region that you're evaluating it. This vector field right here is a vector field that is, in some sense, rotating around the unit circle in the xy plane. So all of the vectors are sort of rotating around that unit circle, which maybe could be characteristic of a magnetic field. If you think of the way that a magnetic field behaves, maybe around a coil, so a single line of or circle of current. If you have a wire in the xy plane, the magnetic field is going to sort of behave like this. And we're still kind of, even for this vector field and any more complicated vector field, we're thinking with the same idea. We take a very small cube. It's a very, very small cube, and we want to consider the flow, right, of mass in our example now through this cube. But we'll see that the continuity equation can actually be used to express conservation of any quantities that are conserved, which is very cool. So back to our example here with the flow of mass through this vector field V, this velocity vector field. And what we want to do is first find an approximation to the total mass entering one side of the cube, one specific face. And what I'll do is I'll label each one of these points. This point we'll call A, this point we'll call B, this point we'll call C, this point we'll call D, and this point we'll call E, this point we'll call F, this point we'll call G, and this point we'll call H. So this is I've drawn a very big cube, but remember this is a very zoomed in picture here. This cube is in reality a very, very small cube. And because it's so small, as long as the vector field is smooth enough, right? It's smooth enough around this point. As we get smaller and smaller with the cube, we can actually get a nice approximation. Specifically, we'll start with the total mass entering the cube at face EFGH per unit time. And this is approximately equal to what? Well, let's try and get in that nice approximation here. EFGH is the back face of this cube. And the total mass entering is going to be exactly or approximately equal to, when delta x, delta y, and delta z are very small, the density times the y component of velocity evaluated at some point. Because this is so small, we'll just choose the back face of the cube right here. So the cube has a front face midpoint here, and then a back midpoint here. We'll choose to evaluate it here at this back midpoint, the velocity here. Because the cube is so small, essentially the total mass entering at EFGH per unit time is going to be the density times the velocity at this midpoint right here. So this is exactly the point. X, y plus delta y over 2, z. Times the area of this face, which is delta y, or delta x times delta z. So we have an expression for the total amount of mass entering at this back face. We want to get an idea of the total amount of mass leaving the front face, so leaving A, B, C, D at this point right here. This is, again, per unit time. And this is going to be approximately equal to rho V2 at, so this value, the total amount of mass entering, plus the change with respect to y in this rho V2. And this is all times delta x, delta z. And simply put here, right, this is just because of, we know that the change in rho V2 over the interval delta y, right, is going to be exactly, if you have, say, a plus b minus a, this is equal to b. This is kind of the idea here, right? If you have an expression for the change in y over the interval delta y, that's what this delta y of this means, or delta sub y of this means here. This value is exactly the correct value at this face. So notice I haven't used an evaluation here at this point. We're going to use what we know about multivariable calculus to get an idea. in a nice simplification here. And you'll see why in 1 second. Remember from multivariable calculus, the concept of linearization or approximation. It's almost the same thing as linearization or approximation in 1D calculus, but say in multivariable calculus, if you have a function of x and y, the change in that function is approximately equal to the derivative of that function. In this case, you'll see the x change in that function is the x partial derivative of that function times the change in x for small values of delta x. And similarly, the change with respect to y of that function is approximately equal to the y partial derivative of that function times delta y. This is for a function of two variables, but this applies equally well to functions of any number of variables. And thus this expression right here is going to be the same thing as, or approximately equal to, rho v2 at the point x, y plus delta y over 2. And now plus, it'll be the y partial derivative of rho v2 at this same point times delta y. All of this times delta x, delta z. Alright, so this is the correct form for writing this, because we're going to see that what we're trying to do is motivate the definition of the divergence the way that we have it. So this is a correct approximation for the total mass leaving ABCD per unit time. This is the correct approximation for the total mass entering EFGH per unit time. And it's definitely important for me to point out why this works. And the idea to think about here is always, the units. What are the units of this expression? Well, we know that rho has units of density, which is mass per volume, or length cubed. The velocity v2 has units of length per time. And then here delta x, delta z, each one of these has units of length. So the ultimate units of each one of these quantities is mass per unit time, which is a nice little kind of like check to make sure that we're kind of going in the right direction here, the correct direction. So the idea here is, well, if this is the total mass entering through this back face, and this is the total mass leaving through this front face, an approximation to the net change in mass per unit time along y is going to be approximately equal to the subtraction of this quantity and this quantity, or this minus this. And if we copy this down, it's a little bit long. You can kind of take all this and this right here and copy it down and subtract them if you want, but you're going to see that this first term gets canceled out here when you subtract the total mass entering from the total mass leaving. So the net change in mass, and this should say also along y here. Along y per unit time is approximately equal to, when we do the subtraction, the y partial derivative of rho times v2 evaluated at the point x, y plus delta y over 2 z times delta x, delta y, delta z. And this is special for a number of different reasons. One of the big reasons here is that it's a relatively simple expression involving the partial derivative. And the other reason that it's special is that you can do the exact same thing here along x and along z, and not much is going to change except for the components. The net change in mass along x per unit time is going to be the x partial derivative of rho times v1, where v1 is the x velocity component. And this is going to be at the point x plus delta x over 2 yz times delta x, delta y, and delta z. And you have a similar equation for z. The net change in mass along z per unit time will be the z partial derivative of the density times v3, and it becomes then evaluated at the point x, comma y, comma z plus delta z over 2. And what this means then is that the total net change in mass in this rectangular prism, right, in this shape, is going to be the sum of these three quantities. So the total net change in mass this is, remember, through the boundary. This is also per unit time. Is going to be the following. It's the sum of these three quantities. So the total net change in mass through the boundary per unit time is going to be the x partial derivative here. And we do have a little bit of a simplification because each one of these has a delta x, delta y, delta z in it. We can just add all these up and bring the delta x, delta y, delta z over and factor it out. The net change in mass through the boundary of this rectangular prism is going to be the x partial derivative of rho v1 plus the y partial derivative of rho v2 on that back face. And then lastly, plus the z partial derivative of rho v3. And all of this needs to be multiplied through by the total volume of the domain itself, delta x, delta y, delta z. But this is the correct approximation to the total net change in mass per unit time through the boundary, right, of this region right here. And this approximation gets better and better and better the smaller delta x, delta y, and delta z are.